This is a video on hypothesis testing. Hypothesis testing is kind of like a debate or an argument. And it's going to have lots of technical ideas, but in the end, we're going to have to decide, do we have evidence to show we're right, or maybe we don't have evidence. So let me show you what we're going to be looking at and all the details. So first, I'm going to talk about something called left, right, and two-tailed tests. That's kind of the idea is, do we think we're on the low side, we're on the high side, or maybe we're just different from what we had expected to be done or what the other guy said was true. Then we'll talk about type 1 and type 2 errors. Those have to do with the idea is you make a conclusion, but maybe your conclusion isn't right. And then you want to think about, well, if your conclusion's wrong, what kind of bad things might happen? Then we'll look at something called p-values and rejection regions. And that's kind of the deep math that we've been talking about in the last few chapters. The p-value kind of tells you the rarity, probability that what you were able to show with your evidence would be that rare if the other guy was right. And a rejection region is the graph. Under the z or the t distribution, we'll have some others too, and that graph is going to help us understand the p-value or the probability, because the probability, if you remember, is the area under a curve. Then after that, I'll get into the details, the step-by-step process in conducting a hypothesis test. And then finally, we'll do some examples. So the first type of example we'll look at is we'll look at a hypothesis test for a proportion. So that's when we want to find out if the proportion is less than or greater than or maybe not equal to some proportion that the other guy is saying is true. Then after that, we'll do the same thing, except we'll look at a hypothesis test for a mean. And we'll find out whether the population mean is greater than, less than, or not equal to whatever the other guy is saying was true. So let's start getting into some of the details. So first, let's talk about the null and alternative hypotheses. I like to think of a hypothesis test as a debate. So the idea is your opponent in the debate says, this thing is true. And you say, no, it's not. That's ridiculous. But of course, we know in statistics, unless you collect data, then you really don't have good evidence to show that the other guy's ridiculous idea is wrong. Okay? So what we're going to be looking at is we'll look at the data and we'll say, well, I think that based on my data, I can show that the other guy is wrong, or at least it's very likely the other guy's wrong. So the null hypothesis is going to be the other guy's statement. And the alternative hypothesis is my statement. So the other guy you could think of as a villain, that's the villain statement, and we're the heroes. So we can think of the alternative hypothesis as the hero statement. Okay, so here's some examples. Let's suppose that you want to find out if more than 50% of voters support a candidate. Because if more than 50%, then that candidate should win. So let's write down the idea or the null hypothesis and the alternative hypothesis. And here's how the symbols work. First, we use the letter H, capital H, to represent the word hypothesis. Now the subscript here is 0, but unfortunately, or fortunately, depending on where you're from, the Brits got to it before the Americans. So we don't say H0, we say H0, N-A-U-G-H-T. So that means kind of the standard, what the other person says is true. We don't think it's true, but we write that down. And in this case, the other guy says, it's 50%. That's the number of voters. Now, 50% isn't enough to win. That's a tie, maybe. It turns out in a null hypothesis, we always write down first the variable, and it's for the population parameter. So remember, the letter we use for the population proportion is P, and for the sample proportion is P with a hat over it. So we write P, and then for the null hypothesis, we're always going to write equals. So P equals 0.5. But then in the debate, we say, no, it's not 0.5. It's greater than 0.5 because my candidate's going to win. And if my candidate's going to win, then the proportion is going to be more than 50%. So P is greater than 0.5. Let's look at another example. Let's suppose you want to find out if the mean number of snowboards rented is greater than 60 snowboards per day. This is different in that in the last one we were looking for a proportion, and in this one we're looking for a mean. Now remember, when we're talking about the null hypothesis and the alternative hypothesis, when we're looking for a mean or a proportion, it's always a population parameter. So let's look what the hypotheses are in symbols. So the null hypothesis, H, and then not, that's the 0, and then not P anymore, because we're talking about a population mean. And recall that the symbol we use for a population mean is mu. So then always equals, and we want to compare it with the number 60. So the other guy, our opponent, is saying, the mean number of snowboard rented is 60, and we're saying, no, it's not. It's greater than 60. So the opponent is the null hypothesis, mu equals 60. The alternative hypothesis, H1, some people, by the way, write an A for alternative instead of 1. They do 0 and A, but I like to write down H1 because then you have 0 and 1, and that seems good in numbers. Kind of 50-50 split in terms of what people use. So H1, and you always put a colon. This guy is not an equal sign. This is a colon, and over here this is a colon. So never ever write H1 equals. It's always H1 colon, which means that there is a statement that follows. That's what colon means. And then mu is greater than, because of this word greater right here, 60. Let's look at one more example, and let's see what we get. Okay, we want to find out if the average speed that people drive on Highway 50 is different than 40 miles per hour. Okay, so here, let's look at some keywords. One of the keywords is average. So we're not talking about a proportion. We're talking about an average or a mean. Another keyword is different. Notice that here we had greater than 50%. Here we had greater than 60. You could also have less than. I didn't do that example, but a less than would be a less than sign. But different is the third inequality sign. So let's take a look at what that looks like. So again, H naught with a colon. Notice those always happen, H naught colon. And then mu, because we're looking at the average. Equal is always what we write for the H naught. And then 40, because we're comparing with 40. The other guy says it's 40. We say, no, it's not 40. So H1 colon mu, and the symbol for different is not equal to. So mu is not equal to 40. So hopefully you have an idea on how to construct the null hypothesis and the alternative hypothesis given a hypothesis test. So let's move on. And let's talk about left, right, and two tails. So we call a hypothesis test a left-tailed hypothesis if it involves a hypothesis that the parameter is less than a number. So H naught, for example, mu is equal to 10. But then when you're talking about left-tailed, that's in the H1. Mu is less than 10. And that's a less than. So a less than on a graph is the left side of the graph. And that's why we call it a left-tailed hypothesis. You might be able to guess what a right-tailed hypothesis is. That means we're going to involve the hypothesis that the parameter is greater than a number. So in this case, the alternative hypothesis is that mu is greater than 10. So when we have the greater than sign, we call that a right-tailed test or a right-tailed hypothesis. And then finally, the third type, which we saw on the last screen, is called a two-tailed hypothesis. So left-tailed means that we're going to say we're right if it's very far left. So very far left of 10, for example. Right-tailed means that we're going to say we're correct if the data shows that it's very far to the right. And two-tailed means that we're going to say we're correct if the data indicates it's either far to the left or far to the right. And in that case, of course, a two-tailed hypothesis test is going to have the not equal to sign. And again, this could be a proportion or it could be a mean. We still use left-tailed, right-tailed, and two-tailed. Okay, let's talk about type 1 and type 2 errors. So remember, a hypothesis test is a debate. So your opponent is saying, I'm right, but I'm going to say, no, 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 I'm right. And the idea is you're going to collect evidence to decide, or at least to support the claim that I'm right. Or maybe you're going to support the claim. Actually, we're not going to support the claim, but we might say, well, we don't really have enough evidence to say I'm right. So it could be the case that I have really good evidence. I have evidence to say that I'm right, but I wasn't. That happens sometimes. Not very often, but it does happen. And you ever been in that case where you said, I'm right, and I know it, and see, look, I looked at a bunch of things, and yeah, you're wrong, I'm right, here it is, and then the next day, you realize you were wrong. And then you have to kind of go back to your opponent and say, yeah, I didn't do it right. You know, I had evidence, I thought I was right, but no, you know, I'm an honest guy, and you were really right. That would be a type 1 error. A type 2 error is kind of the opposite. That means your opponent's saying, the opponent's right, and I'm going to say, no, 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 I'm right, I think I'm right. And then we're going to get the evidence. Then we're going to collect the data, and we're going to end up saying, you know, my data doesn't show it. I took a survey. It doesn't look like I'm right at all. Maybe I'm not right, maybe I'm right, but the evidence doesn't show it. And then the next day you find out you're right, and you go, oh, no, I was right, and my opponent was wrong, and I didn't say I was right. I said my evidence wasn't strong enough. That's called a type 2 error. So, in general, a type 1 error means that we rejected H naught when H naught is true. And the probability of a type 1 error, we use the letter alpha. This is a Greek letter, and that's alpha. Then a type 2 error means we failed to reject the null hypothesis when the null hypothesis was false. And this is a detail we're not going to talk much about, but the probability of a type 2 error is often noted as 1 minus, that's a Greek letter beta, 1 minus beta. So those are type 1 and type 2 errors in general. But let's look at some examples, because that's really when you find out what these errors are all about. So let's suppose that a hypothesis is done to see if a proposed vaccination for HIV is effective in reducing the chance of a person getting infected. Let's discuss the implications of a type 1 and a type 2 error. Okay, so it's the implications that really matter. In other words, if you have an error, errors are never good things. That means you messed up, you collected your data, maybe you collected your data just right, but you just had bad luck, and your data didn't indicate the truth. So what we want to do is we want to find out what will happen. What will happen if our data doesn't indicate the truth? So let's start out with a type 1 error. So a type 1 error means we're going to make that decision. We're going to say that we rejected the null hypothesis, but the null hypothesis was true. Okay, so rejecting the null hypothesis here is that the vaccination doesn't make any difference at all. So the infection rate for HIV with the vaccination or without is the same. So with the vaccination is the same as it has always been, which means the vaccination is not working. H1 means that the infection rate for HIV is less than the infection rate without the vaccination. So if you have the vaccination, the infection rate will be less than if you don't have the vaccination. So then the question is, if you have a type 1 error, why is it bad? So what that means is that we collected a sample, we checked it out, and we looked at our sample, and we said, wow, look at this. In our sample, the vaccinated people in our sample are getting HIV at a much smaller rate than the people, the general public people that we have kind of data from before. And then what are we going to do? We're going to go through and we're going to vaccinate everyone. We're going to say, hey, we have the most amazing vaccination in the world. And guess what's going to happen? We're going to think we're wonderful. We got a great vaccination. And then later on, we're going to realize that this vaccination doesn't work at all. And it does nothing. It does nothing to prevent HIV. So maybe we've given everyone a shot. Maybe we spent lots of money. Maybe people will even feel a false sense of security because they've been vaccinated. And they think, I've been vaccinated, I don't have to worry anymore. And they may have unsafe sex or maybe use bad needles or whatever it might be. So that would be horrible. That would be really bad. Okay? That's a type 1 error. That's the problem with the type 1 error is we make the decision and we say, our medicine works. We vaccinate everybody, and then it doesn't. Let's look at a type 2 error. So a type 2 error means that we looked at our sample, and our sample, it might have been a little better, but not enough to say that our vaccination is really making the difference when it comes to reducing the rate of HIV. And because our sample did not make that difference, then the FDA is not going to approve the vaccination to be given. Okay, remember, this is a type 2 error, which means we failed to reject, so that means no approval of this vaccination. But actually, it does work. So what's going to happen is we have this vaccination that is wonderful. It works. It drops the number or the percent of HIV significantly. But our sample, just for bad luck, maybe we got a bunch of people that engaged in unsafe sex more than other people did. The vaccination would have helped, but we just had really bad luck with the sample. And the vaccination works, and it's never used. Had we had a sample that showed the vaccination worked, because it really does work, then we would be able to reduce HIV, or at least the percentage of people that end up with HIV. And that's terrible also. You notice that's another error. So that's a type 2 error in this situation. Okay, let's move on to the p-value. So as I mentioned in this last example, we looked at this vaccination. So the idea is, if it's true that this vaccination that we're trying to use is useless, and we took our sample, and our sample showed it was lower, maybe, the question is, what would be the probability due to random chance that if the vaccination had been useless, so if H naught had been true, what would the probability be that we would end up with a sample mean that is as ridiculously low or ridiculously high if it happens to be an H naught with a greater than, or ridiculously different? So a sample mean that's that extremely high, low, or different, depending on whether we're doing a left-tailed, right-tailed, or two-tailed test, that extreme result than the sample showed. Okay, let's move on. This is a tough thing, and we'll show examples of this. So here's an example. Okay, let's suppose that a hypothesis test was conducted with 200 students. We'll always use n for the sample size, so n equals 200 students, to see if more than 70% of college students gain weight in their first year of college. Okay, sometimes they call that the freshman 15. You might have heard that before. Maybe we read an article that said that 70% of all college students gain weight in their first year of college. We say, no, that article can't be right. It's higher than that. So H naught would be that P is equal to 0.7, that's 70%. And H1 would be that P is greater than 0.7. So now let's talk about the p-value. Let's suppose that the sample proportion was found to be 0.76. So in our sample, 76% of these 200 students gained weight in their first year of college. Okay, notice that 76% is higher than 70%. But we've learned enough, we're pretty far in statistics, that we know that random chance could happen, and yeah, we got 76%, which is higher. But the question is, had it been 70%, and we did a sample with 200 students, is it unlikely to just randomly get 76% out of these 200? Again, you don't expect usually exactly 70%. It might be a little bit higher. So let's suppose that the probability, the p-value, was 0.03 or 3%. Then this is how we interpret that 3%. It means that if the proportion really was 70%, so if that article we had read really was true and 70% of all freshmen gain weight, and if we took a sample, or if we took many samples, of size 200 students, then 3% of the samples will produce a sample proportion at least as big as 76%. Okay, in other words, we can say that there would be, just out of random chance, a 3% chance of taking a random sample of 200 students that will end up with a proportion of freshmen who gain weight in their first year at least 76%. And that's what the p-value means. Here's the bad news. There's no way of stating this in a very short way. You have to start with if the proportion really was 70%. So in general, if H naught had been true, H naught was that the proportion was 70%. And if you could either go many samples, or if we took a sample of size 200, you could either say 3% of these samples, or there would be a 3% chance of such a random sample would produce a sample proportion at least as large as 76%. So notice that this probability is for sample proportions. Okay? So H naught is for the population proportion, but we've only taken a sample, and we're saying that given a sample, what would be the probability of getting something as extreme as what we got? So hopefully this makes a little bit of sense on what a p-value is. We'll look at some more. Okay, so now let's look at this graphically. And what we'll talk about is what's called the rejection region. So that's the region under the z or the t. We've learned in confidence intervals that we can use z, for example, for proportions as long as np and nq are greater than 5. And also you can use z if you happen to know for means, if you happen to know the population standard deviation, which is really rare. Usually you don't. Okay, otherwise you use t when you're talking about a hypothesis test for a mean and you don't know the population standard deviation. So it's the region under the graph such that a test statistic in that area will result in H naught being rejected, which, by the way, if you reject the null hypothesis, that means you said the other guy is wrong, and if you say the other guy is wrong, that means you're right. So H1 is accepted. So a test statistic outside of the region will result in failing to reject H naught. Now this takes some getting used to. And this is one of those kind of, bad sportsmanship kind of things that we do with hypothesis testing. Never admit you're wrong. All you do is you say that I didn't have evidence to say I was right. Okay, it's kind of a double negative, and it's the way we do things in hypothesis tests. It might be that our sample size was too low. It might be that I was wrong. We really don't know, so we just fail to reject. So let's look at this graphically. So if we have a left-tailed test, then this is showing a normal curve, but a t-distribution is kind of similar. And later on in this class, we'll have some other distributions. Then the critical value would be a z And we've seen this number, negative 1.645. The area to the left of that negative 1.645 is 0.05. So I'm doing the example where we have what's called a 5% level of significance. So what happens is we're going to collect our sample. We're going to calculate the p-value. And if the p-value is over here, okay? So if the p-value is over here, so that means that the area to the left of this value right here, which we're going to call our test statistic, that'll be some value of z. And if the area to the left of that is less than 0.05, so that means that our value of z is less than negative 1.645, we reject the null hypothesis. So we call all of these values here the rejection region. On the other hand, if we're greater than negative 1.645, then we're going to fail to reject the null hypothesis. If it's way out here, we're going to say that it would be very rare to get a z-score so far to the left. So the other guy's wrong, we're right. At least we have evidence to say so. Whereas if we get something out here, that's not so rare. That's a high probability. So we're going to say that we fail to reject. We're not going to say the other guy's right. We're going to say we really don't know who's right. Okay? It's a very fancy way. Fail to reject the null hypothesis. It's a very fancy way of saying that I did a whole lot of work and I know nothing. That's all you're saying. Let's look at a right tail test, very similar. So for a right tail test, we draw the graph such that we shade in the right-hand side of this critical value, positive 1.645. And if the test statistic happens to be over here, which we'll show you in a minute on a calculator, that means the area to the right is less than, say, 0.05, then we're going to reject the null hypothesis. On the other hand, if we're over here and the area to the right is greater than 0.05, then we're going to fail to reject the null hypothesis. And then for a two-tailed test, that means we have a left and a right-hand side. And then you could go to either side. And because we go to either side, we want to say the area on either side in this rejection region should be 0.05. And we've seen this with confidence intervals. If you had, say, a 5% level of significance, which means a 95% confidence intervals, kind of, we use 5% instead of 95%, then that means we're going to split the area in two pieces. 2.5% to the far left, 2.5% to the far right, and 1.96 and negative 1.96 are those barriers. So if we're out here, far left, we're going to reject the null hypothesis. Or if we're far right, we're also going to reject the null hypothesis. On the other hand, if we're in this middle area, we fail to reject. So hopefully the graph makes sense. So let's talk about the order at which we do things. It's very important that you do things in the right order. Otherwise, it is just poor statistics. It's something different. Sometimes we call that data mining. So let me show you the order. The very first thing is we have to determine the hypotheses in words. So it might be, I read that article. The article said that 70% of freshmen gain weight in their first year. And I say, no, I don't think that's true. I think it's actually bigger than 70%. More than 70% gain weight in the first year. And that means all students in the whole country. So the next step, after we've got it in words, is we write down the symbols, H0 and H1. So H0 in that case would be that P was equal to 0.7, and H1 was P was greater than 0.7. After you've written down H0 and H1 in symbols, then what you do is you determine the level of significance. That's the alpha. And the level of significance is determined by how terrible it is for there to be a type 1 error. So how awful would it be if you ended up concluding that more than 70% of freshmen have gained weight in their first year? But really, that's not true. It was 70%. Okay? In that case, you'd probably lose some face. Maybe you'd publish and your publication would be wrong. so you'd be embarrassed. I don't think anyone would die. You may end up maybe changing the cafeteria, convincing the cafeteria director and having them have lower calorie food when really not that big of a deal. And you're going to have students mad at you because you have a bunch of this healthy, not as tasty, delicious food because you're not throwing the sugar in, the fat, when the freshmen can handle the sugar and the fat. Who knows? So that would be the problem with the type 1 error. If you find that's really bad, then you're going to have a level of significance very, very small, like 0.01. If you find that there's really no big deal at all, then you might use 0.1. The standard level of significance is 5%, 0.05. And that's kind of the flip side of the standard confidence level. So 95% confidence is standard, 5% level of significance is standard. Once you've determined the level of significance, then you go ahead and conduct the survey or the experiment. That's actually the hard part. In a course in statistics, that'll usually just be given to you. Sometimes we'll do a project or two, and then you'll have to do that. And that's a lot of work. You have to actually go out and ask people this question. Hey, did you ask them at the beginning of the year and the end of the year? You weigh them and see, did they weigh higher at the end or not? And find out. And that could take a lot of work. It could be expensive. It could take a year to do. So you want to make sure that you do everything else correctly so that when you conduct this survey or experiment, which takes all the work, you've got it right and you don't have to redo it. Then after that, we calculate the test statistic. That's going to be done using a calculator or a computer, and we'll talk about that later. Then after that, we calculate the p-value. So we've talked about the p-value. That is the probability that if H naught is true, and we did another study, that we'd have that % chance that our study would result in something as extreme as what we got. Then after we calculate the p-value, we compare the p-value with the level of significance. If the p-value is less than the level of significance, so if we get a p-value of, say, 0.02, and the level of significance is 0.05, then we have a small p-value, and we get to say that there is statistically significant evidence to say we're right, to say that H naught was false and H1 is true. If the p-value was large, and particularly larger than the level of significance, so if, say, we got a p-value of 0.42, and the level of significance was 0.05, then the p-value is too big. Then we make our conclusion. And in that case, you don't say that I was wrong. Remember, never say you're wrong. Instead, the conclusion you make is that we don't have statistically significant evidence. Sometimes we say we have insufficient evidence, or we say we have statistically insignificant evidence to make a conclusion or to support the claim about H1. Okay, so I like to, a little mnemonic, I like to think of if you go to a restaurant and there's a side dish of peas, do you want to see little nice cute peas on your plate, or do you want to see these gargantuan scary looking peas? I like to have little peas when I order peas for my side dish on my plate. Little peas are good, big peas are bad. So if you have a little pea like 0.0001, that's really little, then we could say we have strong evidence, strong statistically significant evidence to say we were right. Whereas if you have one of those big ugly peas like 0.87, then we say we have insufficient evidence to support the claim. Okay, so let's now look at how it kind of works mathematically. We state H naught and H1. In that case, it involves P, and we've seen some examples. Then we find the test statistic. Now, I'm not going to expect you to memorize this formula, but this is the z-score for proportions. P hat was what we observed. P was our hypothesized value of P. And then if you remember the square root of PQ over N, that was a standard deviation when we had a large sample size. So P hat minus P divided by the standard deviation, observed minus our true proportion, divided by the standard deviation, that was a z-score. And that's called the test statistic. The calculator is going to do that for us, but it's nice to kind of see where it comes from so we can tie it in with all the math that we've been doing. Then we get the p-value, and the p-value is the proportion that corresponds to the z, and the calculator will do that. And in the TI-84, we're going to be using the one-prop z test. Then, if the p-value is less than alpha, reject H0, accept H1, and state the conclusion. If the p-value is greater than alpha, fail to reject H0, and make no conclusion, just say there's insufficient evidence. Okay, sometimes we say there's statistically insignificant evidence. Let's look at an example. So here's an example. A candidate for the upcoming election has done a survey of registered voters to see if she will win. In order for the candidate to win, she's going to have to get more than 50% of the votes. Of the 300 registered voters that she surveyed, 170 of them indicated that they would vote for this candidate. What can be concluded at the 0.05 level of significance? What we're going to do is we're going to use a one-prop z-test. So let's take a look. The first thing is we state our hypothesis, H0, is that p equals 0.5. H1 is that p is greater than 0.5. You have to get more than 50% in order to win. We're going to use an alpha as 0.05. This is standard. In social science, and political science is one of the social sciences, alpha is 0.05 is your standard level of significance. Okay, Gallup poll did this. The New York Times decided that that was standard, and everyone listens to the New York Times, and it became 0.05. So the next step is we need to go to our calculator. So let's go to our calculator, and let's calculate what the p-value is given the information. Okay, so here's the calculator. And what I'm going to do is I'm going to stat. We've seen that button before. I'm going to go to tests. And then, instead of a confidence interval, we're looking at a hypothesis test. So in this case, because we want to take a hypothesis test, or conduct a hypothesis test for a population proportion with a single sample, we're going to go to the one-prop z-test, which is number 5 here. I hit enter, and it's going to ask us some things. So the first thing it asks us is p0. p0 is the proportion that is kind of contained in H0. And if you remember, that was 50%, but we always write as a decimal. That's 0.5. I hit enter. Then it asks for x. X is the number in the sample that said yes. So if you remember, 170 of these voters that the candidate looked at or asked said yes. So 170. And then n, we've seen n before. N is the sample size, and the sample size was 300. There were 300 voters, 300. And then it asks prop not equal to p0, less than p0, or greater than p0. Well, if you remember, our hypothesis test was that we are looking at p was greater than 0.5. So that means that we're looking at a greater than sign, which you remember is a right tail test. I hit enter on greater than p0. Then I go to calculate, hit enter, and there's our p-value. It gives us a few things. The test statistic, in this case, is z, and that's 2.309, etc. The p-value, that's p, is about 0.01. P-hat, that's the sample proportion, is about 57%. 57% is greater than 50%, but then is it significantly greater? And that's what the p-value tells us, the 0.01. So let's go back to our PowerPoint. Okay, so here's our PowerPoint. And if you recall, H naught was that P was equal to 0.5, H1, P is greater than 0.5, and our level of significance was 0.05. And the calculator gave us a p-value, but the question is, can we really use that p-value? And remember, in order to use the normal distribution, remember there was that z there when we looked at the test statistic. You have to have NP, which is the number of yeses, which we had 170 of, and that certainly is greater than 5, much greater than 5. And NQ, which is the number of no's, that's 130. If there are 170 yeses, and there were 300 people surveyed, 300 minus 170 is 130, and that's also much bigger than 5. So yes, we can go ahead and say this p-value is valid. So the p-value was 0.01. And in particular, 0.01 is less than 0.05. Little p's are good, remember that. Okay, that means it would be very rare. It would be very rare for this to happen with random chance. 1% chance, which is less than our definition of rare that we've defined as 5%. So we reject H naught and accept H1. So the conclusion, let's state our conclusion. The conclusion is there is statistically significant evidence to support the claim that she will receive more than 50% of the votes. And this isn't 50% of the 300 votes. We already know about that. This is 50% of the entire electorate that votes for this candidate or against this candidate. So, yeah, she is very confident that she's going to win because the p-value is so small. Let's interpret the p-value. So our p-value is 0.01. So that means that if it were true that she could only get 50%, which isn't a win, by the way, if she could only get exactly 50% of the votes for this candidate only could get 50%, and if another randomly selected 300 voters were surveyed, then there would only be a 1% chance that at least 170, because that's how many said they'd vote for her, of them will vote for this candidate. Okay, notice there's a small percent chance. That's how you interpret the p-value. Notice this is interpreting the p-value. It's not stating the conclusion. The conclusion is, yes, we have evidence to say she's going to win and get more than 50% of the votes. This is an interpretation of the p-value. Now let's interpret the level of significance. The level of significance was 5%, or 0.05. What that means is that if 50% of the vote were supporting the candidate, and remember, 50% is not a win, so if the candidate could only get 50%, and if another randomly selected 300 voters were surveyed, then there would be a 5% chance, that's our alpha, that the new survey would lead us to the false conclusion the candidate will receive more than 50% of the votes. So notice that alpha, this level of significance, is the probability of a type 1 error. So a type 1 error means that if it were true that P was 0.5, if H naught were true, and another survey was done, there would be that 5% chance, the probability of a type 1 error, that we'd end up finding out, or we'd end up concluding falsely, that more than 50% will support her. Notice in this situation, we ended up rejecting the null hypothesis. So in this case, a type 1 error is of concern because, yes, we rejected the null hypothesis. And we have concern that maybe we rejected the null hypothesis, but the null hypothesis is false. Okay, we're pretty confident because we got a p-value much less than of 0.05. But it still could happen. A type 2 error is no longer of concern at all because we rejected the null hypothesis. A type 2 error happens when you fail to reject the null hypothesis, which didn't happen in this situation. Okay, let's look at another example where we're just going to look at the interpretation. We're going to look at the conclusion and not P and alpha. Okay, here's another example. 12% of Tahoe residents were born in Tahoe, let's suppose. Okay, if you know about Tahoe, most of the people who live here are transplants like myself. I wasn't born in Tahoe. Most of the people weren't. Let's say 12% of all residents were born in Tahoe, a researcher wants to see if the proportion at LTCC at Lake Tahoe Community College is different from 12%. She surveys 400 LTCC students and finds that 45 out of them were born in Tahoe. Notice that 12% of 400 is 48. So yes, 45 is not 48. But the question is it far enough from 48 to be able to say that it would be really too unusual to end up with such a low number as 45, which is less than 48, that we can say that this is too unusual to have happened. So maybe this whole 12% is just wrong for LTCC students. So she finds that 45, which is actually a little less than 12%, were born in Tahoe. What can we conclude at the 5% level of significance? Okay, so the first thing is you state your null and alternative hypotheses. Again, it's a proportion. H naught is the proportion of LTCC students, of all LTCC students, so it's population proportion, is equal to 12%. H1 is that the population proportion is different from 12%, so not equal to 0.12. Alpha was 0.05. So we need to next try to find the p-value. So again, I'm going to use a calculator for this. And let's go to our calculator. Okay, so here's the calculator. Just like the last one, I am going to go to Stat, Tests, and then number 5 is a one prop z-test. We had one sample, and we're talking about proportion, and we're taking a hypothesis test, not a confidence interval, so we hit Enter. Okay, if you remember, we want to find out whether or not it's 12% for the population proportion of LTCC students. So I'm going to type 0.12, go down to X, and what we found is there were 45 of them, of the ones we looked at, were born in Tahoe. N was 400. There were 400 students surveyed. And in this case, our H naught was that P was not equal to 12%. So I hit Enter on not equal to P naught. I go to calculate and hit Enter. Notice that our test statistic is negative 0.46 about. That's a Z. And our p-value is 0.64. It's really big. P hat was about 11%, which is not equal to 12%, but it's not that much different. So now let's go back to the PowerPoint. Okay, so here's the PowerPoint. But before we proceed, we better check to make sure that what we did was right. Was our sample size large enough? So we compute NP. NP was the number of yeses, and that was 45. And that certainly is greater than 5. NQ was the number of no's. There were 400 sampled. 45 said yes. So 400 minus 45 is 355. That's much bigger than 5. So yes, we can actually say the p-value is valid, and we can use that z as our test statistic. The p-value was 0.64, which is much greater than 0.05. So we fail to reject the null hypothesis. And the conclusion is that there is insufficient evidence to support the claim that the proportion, and that's the population proportion, of all LTCC students who were born in Tahoe differs from 0.12. So I want to note a couple things. One is this isn't even close. The p-value is 0.64. Have we gotten, say, 0.06, we might think, well, that's hopeful. That's close. We didn't quite get there, but maybe we're still right. Here we're so far away that it might even be a bad idea to even try to do another sample with a larger sample size so that we can kind of show the truth better. When you have a 0.64, a very high p-value, much higher than alpha, you usually give up. Then you usually say, well, maybe I wasn't right. I could have been right, but probably not. I don't think I want to spend a whole lot more time and money to try. On the other hand, if you get, say, 0.06, you would say, oh, shucks, I just missed it. Maybe if I did 4,000 instead of 400, I get it. You can't do 400 again, because if you keep trying, Remember, there's always a 5% chance that you're going to just get lucky or unlucky depending on how you look at it, and reject the null hypothesis when the null hypothesis was correct. So you can't use the same sample size, but you can do a much larger sample size and kind of show the truth a little better. On the other hand, if our p-value is less than 0.05, like in the first example, say 0.01, you don't need to do another example because you've got your evidence. Maybe someone else might want to do because they don't believe you, but you have your evidence and you can publish your paper. And you say, yes, I was right. In this case, pretty much you kind of turn around, put your head down, don't say you're wrong, but say, well, I don't know. Okay? Don't say I'm hopeful, but just say, I don't know. And this is a very fancy way of saying, I don't know. Okay, so let's move on and talk about hypothesis tests for a mean. So it's very similar. We state the null and alternative hypotheses, H0 and H1, but this time instead of H0 and H1 involving P, H0 and H1 involve mu, because we're talking about a population mean. You determine alpha, the level of significance. 0.05 is standard, but sometimes you go higher or lower. We get our p-value. In this case, most of the time we'll use a t-test, and that's because most of the time you really don't know a population standard deviation. In a way, if you knew the population standard deviation, you'd probably know the population mean, and you don't need to do a hypothesis test, you just know. So almost all the time it'll be a t-test. Occasionally you might happen to know the population standard deviation, probably not, and then we'd use a z-test. If the p-value is less than alpha, we reject H0 and accept H1 and state the conclusion. Same idea as we had with proportions. If the p-value is greater than alpha, we fail to reject the null hypothesis and make no conclusion. You find a fancy way of saying you know nothing, that there is no evidence, statistically insignificant. There's insufficient evidence. Lots of fancy ways of saying I know nothing. So let's look at an example. So a study was done to see if the average college student receives less than the recommended 8 hours of sleep per night. The 45 students who were surveyed averaged 7.4 hours of sleep and had a standard deviation of 2.1 hours. What can be concluded at the 5% level of significance? Very similar to what we've had before. Let's start out with the null and alternative hypotheses. H0 is that the population mean number of hours of sleep for all college students is 8 hours. H1 is that the population mean, mu, is less than 8. And we're using a 5% level of significance. So now let's go ahead and go to our calculator. Okay, so here's our calculator. I hit the stat key. I go to tests. I'm going to go to number 2, which is a t-test. We don't know the population standard deviation. Again, you usually won't. And it's just a standard test for a mean, single sample. Now, here it asks for data or stats. In this example, we were given statistics. We were given the mean of the sample and given the standard deviation of the sample. If you have to be given the data from the sample instead of the mean and standard deviation, then we go to data, we put in L1 and L2, or L1 in this case, and then we would go to data instead. And it's pretty self-explanatory, use L1. But we have stats. And we have mu naught. That is what the hypothesis was. Remember, the hypothesis was that the mean was 8 hours of sleep. So 8. We go down. X bar was the sample mean, which was 7.4. Then we go to Sx. That's the sample standard deviation, which was 2.1. N was 45. And our alternative hypothesis was that mu is less than 8 hours. So less than, I'm going to go to less than, hit enter, and go down to calculate and hit enter. And there it is. Notice our test statistic here is t, not z anymore. And that's about negative 1.9. And our p-value is about 0.03. Okay, so here's the PowerPoint. Now, before I even look at the p-value and consider it, I always want to make sure my sample size is large enough. Now, if you remember, the sample size, n, was 45. And it's really important to check. 45 is greater than our benchmark. We're using 30. Some people use 25. I like 30. It's a little safer. So it is bigger than 30. And the central limit theorem says that when the sample size is bigger than 30, the sampling distribution is approximately normal. And then we use the t-distribution for our hypothesis test because we didn't know our population standard deviation, and that's like the t-distribution accounts for that little error of using the sample standard deviation instead of the population standard deviation. So there's our n was 45. We can say that we have a valid test statistic and that the p-value is valid. Our p-value is 0.03, which is less than 0.05, so we reject the null hypothesis. So when we reject the null hypothesis, we say there is statistically significant evidence to support the claim that the population mean hours of sleep that college students get is less than, there's our H1, less than 8 hours per night. Okay, so let's look at the p-value. The p-value is 0.03, and let's interpret it. And what that tells us is if the population mean number of hours of sleep that college students get is 8, so that means that they're really getting the right amount of sleep, and if another 45 college students were randomly surveyed, then there would be a 3% chance, there's our p-value, 0.03, that the sample mean number of hours of sleep for this new survey would be less than 7.4. 7.4 was the sample that we got, and there'd only be a 3% chance, given random chance, had the true population mean been 8, that we would end up with something as smaller than 7.4. Just a note, had this been a two-tailed test with a p-value of 0.03, so had this been a not equal to, then that means you go to both sides. 7.4 is 0.6 away from 0.8. On the other side, if you go 0.6 above 8, you'd end up with 8.6. So had this been a two-tailed test, we would say there'd be a 3% chance that the sample mean number of hours sleep for the new survey would either be less than 7.4 or greater than 8.6. It had our p-value been 3%. Now, it wouldn't be because everything changes a little bit when you have two-tailed tests, but the point is that if you want to find out for two-tailed tests, you have to go left and right. And we're only given the value for left, so you have to see how far is it from 8, that's 0.6, so you go right by 0.6, and that's 8.6. Okay, let's look at the level of significance, which was 0.05, and interpret that. So what that says, again, is if the population mean number of hours of sleep that college students get is 8, and if another 45 students were randomly surveyed, then there would be a 5% chance, that's our alpha, that this new survey would lead us to falsely conclude that the population mean number of hours of sleep per night for college students is less than 8 hours per night. That's the type 1 error. Let's do one last example before we call it a day. And the last example is the following. The average fuel efficiency for U.S. passenger cars is 24.1 miles per gallon. Okay, it must be true because I found it online. Okay, a study was done to see if the average fuel efficiency for cars in Tahoe is different. Okay, maybe it's worse because our cars tend to look like this, big, old, huge. This happens to be a Chevy Tahoe. So the question is it different? Okay, it might be bigger, it might be smaller. I think it probably is worse, actually, but we'll see. The 36 cars that were part of the study had an average fuel efficiency of 22.3. That is different, but is it different enough? Miles per gallon. And a standard deviation of 7 miles per gallon. What can be concluded at the 1% level of significance? Okay, so what we're going to do is we're going to have to go to our calculator. Okay, so here's our calculator. I hit stat just like before. I go to tests. Again, we want to find out about a mean, a single population mean. So I go down to t-test, and I hit enter. We have stats. We don't have data. Again, had I given you the data of the 36 cars, okay, what their individual miles per gallon were, then we would go to data. Okay, we would have put in L1 all the different numbers first, but here to save time, I'm just showing what the stats are. I go to mu naught. Well, in this case, it's not 8. We wanted to find out if it's different from 24.1. So 24.1, that's what the problem stated. X bar was the sample mean, which was 22.3. So I put that in. The sample standard deviation was 7. So I put 7 in. Our sample size was 36. We wanted to find out if it was different, so it's a not equal to mu naught. I hit enter on not equal to, and I go to calculate. So here what we have is our t, our test statistic, is negative 1.54. So we say the test statistic is t equals negative 1.54 about. The p-value is 0.13 about. So let's go back to our PowerPoint and discuss this. Okay, so here's the PowerPoint. And first thing, always check, hopefully you remember, to make sure the sample size is large enough. N was 36. And yes, 36 is bigger than 30. Phew, we can actually do this. So that means the p-value is valid. And we can say the p-value was 0.13, which is greater than 0.05. When it's greater than 0.05, we fail to reject the null hypothesis. Big P's are bad, remember that. Big P's mean we fail. And now we can state our conclusion, that there is statistically insignificant evidence to support the claim that the population mean fuel efficiencies for cars in Tahoe, not just the 36 cars, but all cars in Tahoe, is not 24.1 miles per gallon. Remember, this is just a very fancy way of saying I did a lot of work, and at the end, I really don't know anything. Kind of a drag, but that's what you have to say. But at least, if you're going to say you don't know anything, say you don't know anything with authority. There is statistically insignificant evidence. So that's all I have for today and for this chapter. So I hope you understand it. Otherwise, go through it, watch it again, watch some of the mini videos, go online, find more stuff on hypothesis testing. And we'll move on to hypothesis testing for more than one sample after this in the next video. So thanks a lot for coming, and hopefully this all makes sense. Otherwise, please ask your instructor or ask me, and I'll be happy to help you kind of clarify any difficulties you might have had. Thank you very much. This is the end of the video.